Okay. Okay, so this is 26.6, and we looked at this in video 2 from the work that we did. So in that video we looked at this setup. I'll redraw it here as best as I can. We looked at something that looks like this. Okay, and that was the bridge circuit. I'm going to draw all the resistors in here now. So there would have been one here, one here. And so they were all of resistance 1 except for the bottom right one. So there was I won't put in the units here, but these are all ohms. So this was 1 ohm. Maybe I'll draw it on the inside so I can draw current. So this was 1 ohm, this was 1 ohm, this was 1, this was 1, and this was 2. These junctions here were labeled A, B, C, D. This was a 13 volt EMF. And so what we did in the video is what we followed what the textbook was doing. They had set it up so that they had currents running down here, I1, I2. They set up I3 here. It's going to be a little crowded. And then what they did was they sort of right away applied the junction rule to some of these areas and said, well, if this is I1 coming into A and this is I3 going out of A, well then there must be an I3 or an I1 minus I3 here, right? And then they also said, well, then this must be an I2 plus I3. Oops. And again, the same thing at A, and they came up with an I1 plus I2 here, and then they drew in a bunch of loops. They drew in a loop here where they were going in this direction. They called that loop 1. They called this big loop around the outside loop 2, and they did a loop 3 here, which is hard to draw in there. So what I want to look at today is what if we weren't sort of clever enough to do these junction rules beforehand. Let's say we didn't right away see that this should be I1 minus I3 and that this should be I2 plus I3. What if we just labeled each current on each of these lines 1, 2, 3, and then let's say we labeled this 4 and 5, and we call this current out here 6. Could we then still solve the problem? Let's say we didn't choose the same labeling scheme. So we're going to go through that sort of in full detail here, and we're going to see that yes, we can. And we're going to actually do that solution. So let me redraw this with our new, slightly less clever labeling scheme. So again, it's going to look something like this. Oh, is there an issue with the video? I see a message just came through in the chat. Is anybody else having issues seeing the video? It's fine for you? Okay. Okay. Okay, super. Okay, I was just a little concerned because of the internet issues from Monday. So hopefully everybody can see this. I am recording it and I'm hoping to put it up as well, assuming that everything works out. So so let me get back to this. If the video is very delayed, I guess just do your best, and I can like I said, I'll be posting up the video, so hopefully you can follow along afterward. So I'm going to redraw this. Maybe I'm going to draw it larger this time so we have more space to label. So something like this. This is our source. Okay, so this is a new drawing. We're going to label the junctions with the same letters. So I'm going to call this A, B. We'll call this C and D. Again, this is 13 volts. Let's scroll down a bit. And so again, we have resistor, 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 and resistor. And it's 1 ohm, 1 ohm, 1 ohm, 1 ohm, 2 ohms. Okay, and so just like before, I'm going to use the same labels that we saw before, except we won't do the combination of them. So this is going to be I1. This will be I2 like it was before, and again, this will be I3. But now let's say we didn't right away use that junction rule, and we just said, okay, well, let's just call this I4. We don't worry about it too much. This is I5. We'll call this I6. And so we now have six unknown currents, and let's start putting in our loops that we might want to look at. So we already had this loop before. We called that 1. We had the big loop around the outside, which we called 2. We also had this loop here, which we called 3. But there's also another potential loop that we could have used. Let's label this loop here 4. We could make use of this loop also. So we're going to find that we don't always need to make use of every possible junction and loop that we can to solve the system here. We can see here that we have 4 junctions and we have 4 potential loops that we could use, but we only have 6 unknowns. So in principle, we would think that we could solve the system by only looking at 6 of these, maybe 2 junctions and 4 loops, or 3 loops and 3 junctions or something. But we'll generate the full 8 equations, and we'll see that we can solve the system for our 6 unknowns. But as I said, in principle, you would only absolutely need 6 equations to solve 6 unknowns, okay? So let's get started here. I'm going to generate the equations as we go around. I have them over here. And so I start off by looking at all 4 of the junctions. Okay, so before, this was sort of built in. When we did it in the video, built in, we kind of already included the information from the junctions by doing this relabeling of all the currents. But here, we're actually going to explicitly look at the junctions. So let's say we start off with junction A. So junction A is going to show us that, well, what do we have going on here? We have current 1 coming in, and we have currents 3 and 4 going out. So what does that mean? That means that I1 minus I3 minus I4 has to be equal to 0. Okay. Let's take a look at junction B. In junction B, we have current 2 and current 3 coming in, and current 5 going out. So junction B tells us that we have I2 plus I3. Those are both coming in, and we have I5 going out. Okay, let's take a look at junction C. And this J sub whatever is just a labeling scheme that I'm using. You can do it however you want. I just find it easiest to do it this way. So if we look at junction C, what do we have? We have current 6 is coming in, right? This has to be the same current through here. There's only one path, so this has to be current 6 coming in, and then currents 1 and 2 going out. So what do we have? We have I6 minus I1 minus I2. Okay, that has to be equal to 0 as well. And finally, junction D, we have currents 4 and 5 coming in and 6 going out. So I4 plus I5 minus I6 has to be equal to 0. Okay. And so we'll look at the loops also and generate those 4 equations in a second, but before that, I'd like to simplify these a little bit. So we'll start off with the top one. We can just clean this up. I'm going to isolate I4 on one side, so we're going to end up with I4 is equal to I1 minus I3. If we look at this one from junction B, we'll have I5. I'm trying to isolate the sort of higher number currents because I'm going to be eliminating those more early than the lower numbered ones. So we have I5, and that's equal to I2 plus I3. If we look at the next one, we will have I6 equal to I1 plus I2. And if we look at the last one, we will have I6 equal to I4 plus I5. Okay, so we have that. Let's now clean this up a little bit further. We're gonna substitute in what I4 and I5 are for I6 here in our final equation and see if we can kind of clean that up a little bit. So we can do that, and if we do that, we're going to end up with I6 is equal to, well, if I replace I4, we're going to end up with I1 minus I3 plus, and then the replacement of I5 gives us I2 plus I3. These two will cancel, right? And we're going to end up with an I1 plus I2, okay? And so we see that this is the same as this, right? This is just I6. So these are both the same. So we're getting the same information from looking at junction D, and we get nothing new really. So we don't really need to worry too much about this equation. It's just a duplicate, but we will take sort of these three equations forward with us and take a look at them after we've built our loop equations. Okay. So I'm going to call these. I'll call these let's say A, B, and C capitals. Okay. So now let's go around the loops and generate our four loop equations. I won't be able to have or maybe I can write it really small over here. Let's clean this up a little bit. So this is still a loop. I just want to have a little more space to work over here. So I'm going to write the loop equations over here. So let's take a look at loop 1. So loop 1, maybe do this. Okay, so loop 1, if we start off, we can start off wherever we want, but we'll start off at sort of this side of our EMF. So we're going to start off, we're going uphill, going up across from the negative to the positive terminal here. So we're going to pick up a 13. As we go around loop 1, we're coming in, we go through junction C here, and then we go across this 1 ohm resistor with our current I1 running across it. Since we're going in the direction of the current across our resistor, it's going to pick up a minus sign, but it's just 1 ohm. So we would normally have to write something like minus I1 times 1 ohm, but all of these are 1 ohm except for this one. So I'm just going to drop these, and we're just going to include a 2 when we go across this 2 ohm resistor. So we have a minus I1 as we go across here. Across here we have a minus I4. We're following the direction of the current. And then we go across D, back out here, and we're done, right? And so this is all going to be equal to 0. If we follow loop 2, the big loop around the outside, same idea here. We can start wherever we want. I guess we'll start here at C. So we're going to go across I1, or I2, I should say here, or across the resistor with I2 running on it. So it's going to be minus I2, again, because we're going in the direction of the current. Then we're going to go across this 2 ohm resistor with I5 running through it. So it's going to be minus 2I5. And then we're going all the way around the outside. We go again uphill across our EMF. So that's a plus 13, and that has to be equal to 0 too, right? So we have that loop. If we look at loop 3, we looked at this one before also. So we're going counterclockwise here. Again, we're free to choose any direction we want, any starting point we want. So let's start off here at C. Let's say we'll go across all 3 of these 1 ohm resistors. 2 of them are in the direction of the current. 1 of them is against the direction, so that'll pick up a minus sign. We end up with minus I1 minus I3, so minus I1 minus I3, and then plus I2. And that has to be equal to 0 also. And in this case, we're also looking at our 4th possible loop here. We may or may not need this loop depending on how we set up our equations, right? But we know we have 6 unknowns, so we need at least 6 equations. And we saw that we got 3 equations from, or 3 unique equations from our junctions. So let's write down our 4th loop here in case we need it. So what can we do here? We'll start off at D here. Let's go around this way. We'll go across this 1 ohm resistor against the current, so it's a positive sign. So it's I4 minus I3 minus 2I5. And that has to be equal to 0 too. Okay. So what I'm going to do now is I'm going to go through and just sort of clean these up a little bit and isolate some stuff on one side. So I'm going to go through and look at 1 here. I can't really line them up as I would like to because I don't have too much space, but let's say we let's say we start off with number 1 here. I'm just going to move all the other stuff to the right side. So we'll have 13 is equal to I1 plus I4. For 2, we'll have 13 is equal to I2 plus 2 I5. For number 3, we'll have I3 is equal to I1 minus I2. And for number 4, we have I4 is equal to I3 plus 2 I5. Okay, so we have those equations there. And now, so using these equations here and the 3 equations that we had before, we're going to want to try to solve for some of these variables, right? We want to solve for all these currents, really. So let's do that. I'm going to slide down here a little bit, and I guess I'll add a page. I'm going to have to kind of go back and forth a little bit because we won't be able to have them all on one page at once. But so the step I'm going to do now is I'm going to take all of these values, A, B, and C, and I'm going to substitute in what I4, I5, and I6 are over here. So we're writing everything basically in terms of I1, I2, and I3. Okay, and so this is kind of what would have been done automatically as we generated this first diagram that we looked at in the video. That was all kind of built in as we did that, but we can see that we're going to end up with the same result here. So I'm going to substitute in all the I4s for these values, I5s and I6s, and we'll end up with 4 equations here. So let's take a look at that. So like I said, I won't be able to leave it on screen, but I have them written down over here so we can kind of work with it. So this 13 equals I1 plus I4. What we're going to substitute in for the I4, this I1 minus I3. So let's do that. We're going to end up with well, equation 1 is going to give us 13 equals I1 plus I1 minus I3, right? So that's just I4 having this value substituted in for it, right? And we can see that here. 2 is going to give us 13 is equal to I2 plus 2 I2 plus I3, and this is because we had 2 I5, so we're just replacing the I5. Equation 3 is going to give us I3 is equal to I2 minus I1, and so what have we done there? Well, we've done nothing. We've just kept the same equation because it's already in terms of I1, I2, and I3. It has none of these I4, I5, or I6s in them. Okay, and that's what we're trying to do here. I'm trying to eliminate the I4s, 5s, and 6s to get closer to a solution. For what do we have? We have I4 is I3 plus 2 I5. So I4, so we're going to want to eliminate the I4 itself. So it'll be I1 minus I3. That's our I4 from here. Is going to be equal to I3 plus 2, and this would have been I5, but it's going to end up being I2 plus I3 from our I5 here. Okay. So now I'm just going to go through and clean up all of these, and we'll see that we end up with 4 equations in 3 unknowns that we can work with more easily. So just cleaning up here a little bit, we'll have 13 is equal to 2 I1 minus I3. Okay. Equation 2, as we continue to work with it here, gives us 13 is equal to 3 I2 plus 2 I3. So that's one equation. That's another one. This one we're not touching. We'll just leave that as is, and we'll work with this one a little bit. We can remove the brackets here, so we're going to end up with an I1 minus I3 equals I3 plus 2 I2 plus 2 I3. Shifting things around, we can clean up the right-hand side. We're going to end up with 2 I2 plus 3 I3. And if I just isolate it so that I have only I1 on this side, we'll have I1 is equal to 2 I2 plus 4 I3. Okay, so that is our fourth equation. Okay, so now I'm going to use oh, sorry, did I miss a message? Maybe. Shouldn't it be I3 be I1 minus I2? Let me see. Shouldn't I3 be I1 minus I2? Oh, I think you're right. Did I make a mistake there? Let's see. Okay, so we have I3. This came from number 3 here, and so we would have I3 would be shifted over, and it would be I2 minus I1. Yeah, that's right. So that would be I2 minus I1. Shift that. Sorry about that. And so, oh, this might have made some issues down here. I2 minus I1. Okay, but that's what I wrote down here. Okay, sorry about that. Yeah, so there was a little bit of a mix up here, but it kind of worked itself out down here. So we actually do have I3 as I2 minus I1, right? So up here is where the mistake was, not down here. This is actually the equation that we want. So we're left with these four equations. The plan now is going to be to use this equation that we have here to eliminate I3 from equations 1, 2, and 4. Okay, so we'll just substitute these in, and so this is how a lot of these sort of problems go. Either you can see a sort of clever way in the beginning to clean things up, like we saw here, kind of, and maybe there's even more clever ways to clean it up, or you have to kind of just plug and chug all the way through, and there's a bunch of equations you have to solve, and it gets kind of messy, but at least it's very sort of procedural. So you just follow one step, you follow the next step, you're eliminating things from your equations, and you're basically just solving a system of however many equations you may end up with. Okay, so this is kind of the most labor intensive, but the most straightforward, I guess, in a sense, way to do this. So as I said, we're going to use equation 3 here to eliminate all of the I3s. So let's go through and do that. So now we're looking at equation 1 again. We're going to end up with 13 is equal to 2I1 minus I2 minus I1, right? Because we're moving this I3 in here. Clean that up a little bit further. We end up with 13 equals 3 I1 minus I2. That kind of doesn't look like an I. Okay, so that's one equation. Call this one star. 2 is now going to give us 13 equals 3I2, and we're going to have plus 3I2 plus 2, and now we have I3, so we're substituting in for I3. That's I2 minus I1. We can clean that up. We get 13 equals 5 I2 minus 2 I1. Okay, call that equation double star. And now let's look at number 4. Equation 4 that had come from our fourth loop. We have an I1 equals 2I2 plus 4I3, which we're now going to replace with, with I2 minus I1. Okay, so if we expand that out and clean it up, we're going to end up with, or I guess I'll do it in 2 steps. We're going to end up with this equal to 2I2 plus 4I2 minus 4I1. We'll shift all the I1s to one side, and so we'll end up with 5I1 equals 6I2. Okay, and that we'll call equation triple star. Okay, so we have these 3 equations. That's all we have left. We have 3 equations in 2 unknowns. So we're kind of really getting down to to being able to solve for these values. We're getting down to a point where we have clearly more equations than we need to solve for the number of unknowns that we have. So let's just solve for one of them. Let's solve for I1. We can do that simply by looking at equation 3 stars here. So if we just isolate I1, we'll have I1 in terms of I2. So we'll have I1 is equal to 6/5 I2, and then we can just plug this result that we got from our 3-star equation here back into one of these. Let's say we put it into either one, doesn't really matter. So we're going to end up with 13. So we're replacing let's say we're replacing this one here in 1 star. So we're going to have 13 is equal to 3 times I1. Well, that's just 6/5 I2 minus I2. So this is going to be equal to, it'll be 18/5 minus 5/5 I2. And so we end up with 13/5 I2 is equal to 13. So if we clean that up, we'll have 13 is equal 13/5 I2, which means that I2 is equal to 5 amps. Okay, and is this what we found before? Is this the same current that when we did the example, we found the same current over here, that it was 5 amps? It is. If you look back in the notes, we did find 5 amps there. So now we can just go through and finish it off. We can solve for let's say I1. We can just use triple star again. So let's say we have I1 is equal to 6/5 I2. Just plug in the 5 amps, and we're going to find that I1 is equal to 6 amps, which is the same thing that we found as we did it before also. And finally, if we use I guess we can use whichever one of these we want, but in the end we can use equation 3 that we had earlier, right? So we can use this equation to solve for I3 now. Just substitute those two in. I2 was 5 amps, I1 is 6 amps, so I3 will have to be minus 1 amp, right? And so what does the minus sign mean? The minus sign just means, again, that we chose the wrong direction for our current. So really the current points in this direction, and it's 1 amp. That's fine. We don't have to change anything. We just know that it's pointing in the other direction. And now I won't bother to go through and calculate what these other ones would be, but we can see we have I1, I2, and I3, so we can easily substitute in here and solve for I4, I5, and I6, and we would find that it gives us the same values as we would have found before. Again, before they were written in terms of I1, I2, so we would have had to do it anyway here, but here we just have it written down in terms of these junctions. Okay. So that is that's basically how you would solve this one had you not sort of made those clever substitutions in the beginning. And this procedure for sort of looking at these junctions and these loops is the way that you would solve a lot of the problems in the assignment, and basically most of the stuff you're going to run into in this chapter. There's certain other sort of techniques that we can look at to solve some of them. But oftentimes it'll just be easier to go right to these loop and junction rules, these Kirchhoff's rules, and actually sort of solve it that way. I will mention one more thing before we sort of move on and I open it up to questions. So we're running into a lot of these situations where we have many equations in a bunch of unknowns and we need to solve them. For anybody that has done linear algebra before and is comfortable solving things using row reductions, like using, and if you don't know what I'm talking about, that's totally fine. Many people will not have done linear algebra before, but if you have done linear algebra, which is a math course offered at U of V and other universities, but if you've looked at this stuff before and you're comfortable solving systems by using row reductions and moving things into row echelon form, by all means, go ahead and do that. You can use those techniques. You can use your calculator to solve those systems using those techniques. Just show me the matrix that you're solving, and I'm also fine with that. So yeah, if people have questions about solving these systems using linear algebra, I can answer some of those, but I don't want to go into a whole sort of lecture. And well, I mean, it's basically a whole course on how to solve, you know, systems of linear equations. There's more in the course, but one of the main themes is that that's a way to solve things. So I don't want to do the whole sort of course here, but if you guys have seen it before and you need a little bit of a refresher, just let me know and we can talk about it. Okay, so I will maybe, let me stop recording this because I'm trying to save this, or have I stopped recording it? One sec. Recording in